just get started. So I put this up originally just in case people want to get the Git repo for their own machine and also potentially get Gephi to do any of the graph visualization. So you can go ahead and do that, while I do the first part of the talk. But I'll do like a little bit of talking at the beginning, and then we'll get into the tutorial, and we'll see how far we get in the tutorial. Hopefully there's time for all of it, but if there isn't, I will be around all day today as well as tomorrow. So please come and find me, and we can sort of work through any issues or questions that you might have. So let me start at the beginning. So I did my graduate work at UC Berkeley working with Mark Disposito and Michael Silver, and then I did a postdoc at WashU working with Steve Peterson. And I just started my own lab at Northwestern. So it's particularly great to be here and see all of you sort of learning all of these important tools that I'd also like to sort of get all of my students working on in my lab. And that's what I'm hoping to learn from all of you, and how to encourage people in the spirit of the Slack channel of things that we want to know. I want to know, how do you get other people to also sort of buy into this in your community? But in my talk today, I'm mostly going to talk about the work I've done looking at how do we measure human functional brain networks. I'll give a little bit of general background on what we mean by functional brain networks and some basics of what these measurements might look like, at least in a simplistic sort of way. And then I'll focus a little bit more on a tutorial and sort of getting you started on how to do this. And I saw from the poster session yesterday that several of you are already interested in these methods, which is great. So I probably don't need this introduction, given that, for this audience, but just to sort of set the context, there's a long history in psychology and neuroscience and neurology of thinking about the brain in two fairly different ways. So on the one hand, a lot of time is focused on trying to understand the specialized processing that might go on in different brain regions, how, for example, individual neurons or regions might be tuned for different types of information. But on the other extreme, a lot of people are also interested on how different brain regions may interact with one another. And so I've focused more on trying to understand the large-scale systems or networks, I'll use those terms kind of interchangeably today, how they're organized in the brain and how they change over time and across different contexts. And of course, I think in a broad sense, it's really interesting to try to tie these two levels of investigation together. Today, I'm just going to focus on the coordinated interactions part, but I think that's a really interesting direction to go. So, as I said, my talk is going to be focused first a little bit on background, and then I'll say a little bit about some very recent work we've been doing, looking at recent forms of variation in functional brain networks, and then I'm hoping that we'll dedicate a good chunk of this to the tutorial itself. And you can either clone the repo directly, so the address is here, or you can log in and run it from the Jupyter Hub. I think the PDF of these slides might also be available soon, if not already, at some point. Perfect. So I just sent them to Ariel. So at some point, those will also be available. Some of the tutorial will use this graph visualization software, Gephi, so you can go there and download that as well. You'll need all the plugins that go with it. Please feel free to ask questions. I know people are at various different levels of their experience with functional connectivity, so regardless of your level, if something doesn't make sense or if you have questions about applications that you've used that haven't worked, just raise your hand and I'm happy to sort of go in that direction. Okay, so a little bit of background. So for the experiments I'm talking about today and the data set you'll use in the tutorial, we're using data from functional magnetic resonance imaging, or fMRI experiments. So in those experiments, we're using the blood oxygen level dependent signal, which is a signal that generally increases with increases in neural activity. Now, the reason that I use fMRI for a lot of the network studies that I do is because fMRI has this really nice feature that it allows you to collect measurements from everywhere in the brain at once, which makes it really well suited to measuring large-scale brain networks at a modest temporal and spatial resolution. But of course, and I think as I saw in the poster session, you could also apply these techniques to many other types of time series that you might get from other measurement techniques like EEG and MEG, ECOG signals, optical signals, or even neural recordings. And so when we talk about functional brain networks, the term functional connectivity often comes up, and many people have a love-hate relationship with this term. For better or for worse, it's sort of become the mode. And really often what we mean by functional connectivity is just that we're taking some measure of association or similarity between time courses or activity in different brain regions. So in the simplest sense, if we measure the bold activity, for example, in left and right motor cortex, over time, we can plot those time courses as is shown here. And you might see that they look very similar to one another. They have a very high correlation with one another. And so we might then say they have high functional connectivity or have a functional connection. Another region, like that of left visual cortex, may instead show a very different time series, have a much lower correlation with the motor cortex region, and show a different pattern. So what's somewhat surprising to people is that you can find these sort of associations between left and right motor cortex, not just when someone is moving or thinking about moving, but even when a person is sitting there like a lump at rest. The spontaneous activity in these different brain regions shows correlation patterns. And so you can actually get really rich information during a resting state about the large-scale network structure of the brain. And so the left and right motor cortex show correlations with one another, but not just not with each other, but also with an extended set of regions across subcortex and the cerebellum. Moreover, we can do this not just with those motor and visual 3 regions that I showed you on the previous slide, but many different regions spread throughout the brain. And one way that we often look at this is in the form of a correlation matrix. So in this matrix, which is region by region, any given cell just represents the correlation between a pair of regions. Here I've arranged the regions randomly so that it's hard to see much structure in this matrix. But if I reorder the regions, so I place regions that are part of the same system close to one another, you see this really beautiful structure emerge, which is often called the block diagonal structure, where you have high correlations along the diagonal. So you can see, I have a pointer here. There we go. So you can see high correlations along the diagonal, that is within a given system, and low correlations in the off diagonal, that is between different systems. And so because of this structure, we can then apply a variety of different types of community detection algorithms to identify the systems of the human brain in a data-driven fashion. And so I can just mark off what one algorithm finds here with different red lines, and then paint them on the brain in colors as shown here. So I think one thing that's quite remarkable, if we step back, this has now become commonplace, but it really is quite remarkable, I think, that we can take these measurements at rest and use data-driven techniques and recapitulate a lot of what we already knew about brain network organization. So we get systems like the visual system and the motor system that have been studied for many years, as well as higher level systems like the default mode system or the frontal parietal system, as shown here. Moreover, in recent years, the envelope has been pushed in terms of how well we can do these measurements, not just at the level of large groups. So that previous slide was based on 120 individuals averaged together, but even on the level of individual subjects. So here I'm showing you 4 individual subjects that were part of a data set called the Midnight Scan Club that I'll talk about more later. And you can see that we can get a lot of rich information about the network structure of these individuals. Now, in addition to sort of painting a nice picture of brain network organization at the level of individuals, what else is useful to gather from functional connectivity techniques? Well, one nice thing about functional connectivity approaches is that they allow you to sort of study the brain as a complex system. So adopting tools that have already been used to study many other complex systems, like social networks or metabolic networks or air transportation networks, can also be used to study systems like the human brain. So we can go from thinking about sort of the anatomical organization of the brain to instead representing this anatomical organization as a graph, where different brain regions are nodes in this graph, and functional correlations between these brain regions are edges in this graph structure. Now here, I've still plotted this graph in a roughly anatomical sort of space, so it can be hard to discern the systems that are present because they might be spread across fairly large brain areas. But I can replot this organization in what's often called a spring-embedded or force layout, where I place the nodes that are more strongly interconnected with one another closer together, and that allows you to see new properties of the graph structure. So, for example, it allows you to see properties of the graph as a whole. You might note that there is some substructure and clustering within this, with this visual system, the default mode system, clustering separately from one another and coming off the side. And it also allows you to see properties of individual nodes as they might pertain to this complex system. So for example, you might note that some nodes seem to lie in between different networks, and perhaps you might hypothesize that these nodes may then be important for transferring information across different systems. And so these are different ways that we can try to quantify complex systems hubs within this structure. Okay, so that ends the really brief background, and next I want to talk a little bit about some recent applications of these techniques. So these approaches have generated substantial excitement in the field and kind of growing interest in the ability to use these techniques to address many different types of questions, ranging from how do functional brain networks change with damage and disease? How might they reflect individual differences in behavior, trait-like characteristics? How might they change over the course of the lifespan from development all the way through aging? And how might they respond under different cognitive contexts or with different cognitive demands? And different paradigms have been used to now try to address these questions. And so I will roughly split them into two categories that I think are becoming quite popular nowadays. So the first category I'm going to call the many subject data sets. And so the Human Connectome project is probably the most famous of these. I know you used some of their data yesterday. So this is the idea that we can collect a lot of data from a lot of different individuals, about 1,200 individuals in the young adult data set. And so use that to gather more and more information about individual variability across the population. And of course, that's now being expanded to many other data sets. So some of you may be familiar with these or be interested in using some of these in your work across many different parts of the lifespan, as is shown here, as well as in different disease states. And is even growing proportionally larger with the ABCD project getting longitudinal data from 11,000 plus subjects in their adolescent years. UK Biobank gathering resting state data from about 15,000 subjects, I believe, and so forth. 25,000? Oh, okay, so I'm a little outdated on this. and there are many others as well. So I'm only noting a few of these projects up here. The opposite extreme, I would say, is the approach of what's sometimes called high sampling or deep phenotyping or precision approaches, which is shown here. First inspired by Russ's work on my connectome. So I know he gave a talk earlier. I don't know if he talked at all about any of this, but he took himself and he scanned himself twice a week for a year. And so in this data set, which is publicly available, you can now get really rich information, not only about his resting state networks. There's 80 sessions over the course of this year that have really high quality data, but also about a variety of other phenotypic variables. He had blood draws and so forth, so that you can sort of better understand this single individual. And so, inspired by that approach, other groups have followed suit. So the data set I'll talk a lot about today is the Midnight Scan Club data set. This has not quite as much data, but more individuals. So it has data from 10 different subjects who each participate in 10 functional MRI sessions, as well as additional structural MRI and behavioral sessions. And in the last 2 years, there's kind of been a rapid growth in groups that are using these techniques to try to better understand single individual data sets. And so I'm just noting a few of the examples here. There are, I think by my last count, something like 12 plus data sets that have really rich information on single individuals, and about half of those are publicly available through various sites. So focusing a little bit more on the Midnight Scan Club data set, because we'll use that in your tutorial. So this data set contains data from 10 different subjects who came in for 10 different fMRI sessions at midnight, hence the name of the data set. Not because they were interested in studying people at midnight particularly, but because the scanner was discounted 90%, so the data set could be collected at a very small fraction of the normal cost. But yes, so that gives the name for this data set. So these participants, when they came in at midnight, they did half an hour of resting state fMRI. They were real troopers. That's hard to do. And they also completed a number of other tasks. So they did a motor task. They did mixed block event related tasks, one of which was a noun verb judgment and one of which was a dot coherence task. And then they did an incidental encoding task, which had faces, scenes, and words in it. In addition to that task data, as I mentioned, they also completed a number of other behavioral measurements and structural measurements in other sessions. So what is the value of collecting all of this data from just a few individuals? Well, first off, it allows you to provide these really beautiful pictures of what the brain networks might look like in these individual subjects. So I'm just showing you the plots from the Gordon paper here with the group average network shown in the top panel. Let's see, up here. And then each individual subject shown here in different rows. Or side by side, I guess. And what you can see is that while each individual looks like the group in several ways, so everybody has a frontal parietal network, everybody has a default mode network, everyone has the visual system, as we would hope, yet there are clear distinctions between these individuals in the group, and there seems to be a more rich sort of pattern of information that we get at the group compared to the individuals. So just to highlight what one of these individual differences might look like, so if we look, for example, at the group average in this chunk of the frontal part of the default mode, we tend to find a large swath of cortex that's default mode, colored all red. But in individual subjects, many subjects show patches that are part of what appears to be a separate network. And so this has been labeled as a separate network by community detection algorithms, but we can sort of interrogate this further to convince ourselves that it truly is a separate network. And so we can just place a seed and look at the functional connectivity of that seed in this location between that individual and the group. And what you'll note is that near the seed, of course, the correlations are all high. That's pretty typical. But if you look at the more extended whole brain network pattern, it's actually quite distinct between these two locations, with this individual showing almost no functional connectivity to other regions that are commonly part of the default mode, like the posterior cingulate, like the angular gyrus, and so forth. So leading to the idea that this region in this particular individual may look different than the group average. So in addition to sort of making these beautiful maps at the individual subject level, other things that have been done and can be done further with this data is to then look in more detail at the complex systems organization within these individual subjects. For example, in these subjects, there's already evidence that there's differences in the efficiency and the hub distribution across these subject brains. I think another thing that's really valuable about these precision approaches or deep approaches or whatever you want to call them is that they also give us a test bed to understand better the reliability of the techniques that we're using. So you can come here and use these sort of data sets to test whatever metric you have of interest and try to better understand how much data do I really need to get asymptotic reliability and to make statements about a given individual for that in another context. So for example, one pattern that we've shown in a few different data sets, and here these lines each represent an individual subject, is that you tend to need something like 30-ish minutes to start to reach asymptotic reliability for functional correlation matrices as a whole. And then lastly, another thing that I think is only in its nascent phase, but we're sort of looking to do more of, is to better understand the relationship between these resting state intrinsic networks and activations across individual subjects. So this is just overlaying the motor systems as well as activations in the motor task within the Midnight Scan Club. Moreover, because the data set has data from these 10 subjects across 10 sessions as well as different tasks, this is a nice data set to start to probe questions about how variable functional networks might be across different time scales and contexts. So for example, we can ask, is resting state data more variable across people, or is it more variable across days, or more variable depending on what people are actually thinking about? That is, what are they doing in the scanner? And so this is another question that we've looked at in a recent paper, and the basic sort of summary is shown in this figure here, which is to say that functional network measurements are dominated by stable factors. So they're dominated by similarity that's common across the group in terms of their network organization, as well as individual specific features. And there are only more modest effects of day-to-day variability or task-related variability. Interestingly, the biggest part of the task-related variability is actually individually specific. So it seems to have an interaction between individual differences as well as task-based differences. Okay, so that ends my part of like speaking at you. And so now hopefully we'll do stuff together unless anyone has any questions on that first part. Okay, so, yeah.
Do you think that the proportion of variability group, individual, and is that proportion specific to fMRI, or do you think that that kind of proportion we find in other imaging techniques or
Yeah, I think that's a great question. I mean, certainly fMRI is very slow, especially functional connectivity. We purposely, bandpass filter to get the slowest frequencies, so we may purposely be not getting things that vary at faster timescales that might be related to sort of ongoing cognition or diminishing those effects. I would guess that you'll still have a lot of individual variability even in other techniques, and even with EEG, when you want to look at ERPs, so the things that are sort of linked to particular events, you have to average usually, and it's dominated by these larger effects, but I haven't actually done that work.
It'd be fascinating to see that's like almost like a general rule across
like temporal timescales, yeah.
Because if it's always like almost like a third to third, like a kind of thing. It's a very good number to have in your mind.
Yeah, and the exact proportion did vary a little bit depending on the scale that we looked at. So we looked at, for the whole correlation matrix as a whole, this is done, what's plotted here is actually per region, kind of by row of the correlation matrix. I also looked per edge, and it varied a little bit in proportions, but it wasn't that far off sort of those numbers. Yeah. Yeah. So in the tutorial, we're going to follow along and be able to sort of replicate a few of these things. And as well, you'll have access now to some of the Midnight Scan Club data. So maybe in sort of next week, if any of you are interested, you can take this data and do what you will with it and hopefully find fun and new things to investigate. But for the purposes of the tutorial, I thought I'd start with just a few simple ways of looking at your data that, while simple, may also be quite informative. And so some of you may be very familiar with these, but it's never a bad idea to sort of review and go back to basics. And for those of you who are new to this, hopefully you'll kind of bring up questions as you have them. And so let me go to the actual tutorial. We're going to start with actually looking at the data before we've made functional connectivity measurements. Okay. So as I said, this tutorial is going to be based on Midnight Scan Club data. I've provided kind of chunks of the data for the tutorial, but you can also go to, I now realize I still have the old link at OpenFMRI, but it's also an Open Neuro to get this whole data set for yourself and do what you will with it. And then this paper describes that data set in more detail for anyone who's interested. So we'll just go ahead and start. Does everyone have this open or need the link again? Okay. We're just going to import some libraries that we need and set up some directory structure. I have actually not used Jupyter Notebooks that often. So I have set this up more as a separate script that we've now put into a Jupyter Notebook. The script is also available if you prefer doing things that way. And we'll open sort of files through a Finder window as well. But you can sort of scroll through and see which way you like better. But because it saves out files, it'll do that in this output directory within the folder where you run this, just to let you know. Okay, and so here you can sort of set what things you want to do. Okay, so the very first thing I want to do is plot some what I call gray plots, other people call carpet plots. So these are plots that were developed by Jonathan Power when he was at WashU as an approach to try to interrogate the quality of your data, and I think it's also just a nice approach to better understand what different processing steps are doing to your data. How many people here have ever made carpet plots or used carpet plots before? Okay, so a few, but not everybody. So hopefully those of you who have done it can sort of speak up of what you've found useful about them, and everybody else can speak up about any questions that you have. So if you're interested in learning more, there's this paper that Jonathan wrote in NeuroImage. That's a paper about a plot, which I don't think I've ever seen before, but it provides a lot of detail on it as well. I think fMRI Prep also provides a way of creating gray plots already on its own. I haven't personally used it through that, but it seems like a quite nice approach also. And so this is what it's going to look like at the end, so I just want to show it to you to start with. And one thing that I like about, or one of the reasons I wanted to give you the code, is that it's also really easily customizable, so you can change these gray plots to show whatever you want it to show. The heart of the gray plot is, of course, this thing down here, which is basically a bunch of time series stacked up on top of one another. So each of the rows is a time series from a different part of gray matter, and then over the x-axis is showing time. And so these plots can then allow you to see certain features that are kind of globally spread out throughout your data. For example, you might notice vertical lines that are present in your data. That is common features that are present across all gray matter regions in the brain at a particular moment in time. You might also, and I don't think this data shows too much of it, but if you had, say, bad regions of the brain where the signal was lost or other things of that sort, you'd then also notice horizontal lines, so it's an easy way to detect sort of signal artifacts in that sense as well. And then you can sort of customize this plot to show other features as well. So one thing people often like to do is show the white matter and CSF signals, since those are often used as regressors to clean up the data, and so you can plot those below. And actually, I think Jonathan has changed the way he plots these in some of his papers as well to show the white matter signal progressively further from the gray matter, so you can see that there are gradations in how much shared signal there is between white matter and gray matter. Then up at the top, what you'll often find is other signals that we think might reflect artifactual signals. So for example, I have here the 6 original motion traces plotted in the first plot. And then in the second plot, I have the frame-wise displacement trace, which is often used to identify frames where there's a lot of motion compared to the previous frame. That's in red. The black line shows the place where we often set our threshold for saying a frame is bad or good. And then things like the global signal, which is shown here in green, and the DVARS signal, which is sort of a frame-to-frame change in the gray matter signal over time. And so all of these things can be made in your plot. So let's go back and actually create some of these. Any questions? Okay. So the first thing we're going to do is take the first subject, MSCO1, and make these plots, and we're actually going to make them at several different stages of processing. So you can see what each stage of functional connectivity processing is doing to your data. So before this is done, the data has been slice time corrected, it's been sort of rigid body realigned, and I'm trying to think if there's anything else. Not very much has been done besides that. And so then we will do things like demeaning, detrending the data, regressing out nuisance parameters, interpolating over bad frames of the data, temporally bandpass filtering the data, and then another demean and detrend at the end. So run that. And it's going to make a ton of plots in here. You can scroll through or open them up, as I said, in a separate window. Okay. So first off, stage 1, there's nothing in the gray plot. You might be surprised. The way I've set up the gray plot right now is it assumes, the other thing that's been done is the data has been mode 1000 normalized. But this, the way the gray plot has been plotted is it assumes that it's zero meaned. So that's why it's totally zeroing out the color scale. Later plots will show you plus or minus 2% signal change from a zero mean. And so one thing you'll note that compared to the plot I showed you before is, you can't see your gray matter, your global signal, or your DVR signals. Those will change, of course, as you do different steps of the processing. And so one thing to note is that when you choose to, say, maybe use DVARs or a metric of that sort, you might have to also choose which stage of processing is most relevant of those signals to actually use to remove artifacts from your data. Oops. So this is the kind of first step, demeaned and detrended. You can start to see different aspects of your data. You'll notice that when there are large movements, they tend to coincide with these sort of vertical stripes that you get in your gray plot, indicating something has happened to your data that changes it. But when you do nuisance regression, so in this case the nuisance regression included a white matter CSF and global signal motion parameters, derivatives of those, and the Friston expansion of those, you'll note that some of these go away. So you can kind of flip back and forth and go back and forth and see some of the sort of vertical and horizontal qualities of these lines has been taken away, and you get this sort of less structured picture at the end. In this stage, what we do is actually just identify frames that we think are bad, and we interpolate over them in a fashion that maintains the frequency spectrum of the data. So that's just what's happened here. And then this has been bandpass filtered. And so, of course, between before and after bandpass filtering, you'll notice that along the x-axis, everything looks smoother. So that's what it's supposed to do. From about 0.01 to 0.1, the exact numbers vary. And then just demeaned and detrended. So okay, so we can kind of do this. You can also do this for different subjects, which I think is what's going to happen in part B. And so here I'm just plotting a gray plot from the final stage of processing from each of the subjects. And so you could use this sort of approach to then see, have you really sort of gotten rid of everything you want to get rid of in terms of the structure in these gray plot time series in each subject. So for example, we can scroll through, I guess this is actually the same subject, different session, sorry. And you can sort of see the quality of the gray plot. You'll notice that there is a variability. So, you know, in this session, the subject I think was falling asleep towards the end, and so you tend to get a lot of movements. It's common that you get a lot more movements towards the end of long runs especially, whereas other runs look like they're higher quality. Okay.
Do you see on Google Forms based on your visual QC or what?
Yeah, I think there's like different strategies. So one thing is I always, like pretty much in every data set, even if they're big data sets like the HCP, it doesn't take that long to do this sort of thing and just like scroll through and just make sure, like, is there anything crazy going on in your data set? And sometimes you will find, actually in the HCP, I think not infrequently, you'll find kind of weird things happening that might reflect like scanner malfunction or other things of that sort. I think this is also a nice technique for maybe you're testing out different sort of pre-processing streams and you want to see whether your pre-processing stream might be sort of do better at removing or getting rid of some aspect of the artifact that you want to get rid of. And so I think this is just a nice, very nice visualization. Here we only had the motion parameters to play with, but if you have, say, respiratory parameters or heart rate parameters, those are nice other subplots that you could add to the top and might give you other pieces of information of other things that you might, say, want to remove any signals that seem really strongly correlated with those respiration signals. Yeah, I think it's just a useful tool. Functional connectivity is very susceptible to various sorts of artifacts, and so it's a nice tool to look at your data before you actually start doing more complicated things with it. Okay. So now that we maybe have decided we're happy with how what our data looks like, sorry, actually let me, yeah. I put some references at the end of that section, so if you're interested in reading more about pre-processing strategies or these plotting strategies, that might be a place to start. I also want to highlight that another thing you can easily do is look at correlations between your, say, time series or functional connectivity signals and different metrics of data quality like motion. And so this CIRIC paper from Ted Satterthwaite's group does a very nice job of comparing many different processing streams and looking at what each of those processing streams is doing in terms of removing correlations with motion in your data. So I definitely encourage you to look into this paper. I think they also have recently put together a package that allows you to sort of use their package to do that quickly and easily in your data set. Okay, so the next thing we're going to do is actually look at some correlation matrices. So in the interest of time, I had at the beginning, you can take a couple time series and just plot them for yourself and convince yourself that some time series are correlated and some time series are not. But we'll just sort of make these plots that look like this, much like the one I showed you in the presentation earlier, where again, any given cell is just the correlation in the time series between two different brain regions. So let's just run those sections. And so it's pretty simple at this point once you've sort of done all that processing on your data, at least in the approach that we often use, which is just taking correlations. Of course, you could do ICA or coherence or other steps to look at measures of association as well, which would differ a little bit from this approach. But in this approach, we end up with 333 time series. Each of those time series is just an average time series for a given brain region. And then we also end up with a mask of what we say this is low motion data as opposed to high motion data. And so we just apply the temporal mask to the time series data and then do a correlation among those time series. And so we can run that. And again, what happened here? Oh, I forgot to run this. You have to load some information first. So first, let's load some information, which is these 333 time series from each of the subjects, and sort of arrange them the way you want. And then we'll plot them. There we go. Okay, so this is just sort of replicating what I was showing you at the very beginning of the presentation, which is if you order your ROIs in a not sensible way, it's hard to see a lot of structure in these correlation matrices. So they can be more or less useful depending on the ordering of the ROIs. So that actually can matter quite a bit. If instead you order your ROIs in a way that you think is more sensible because you put things that are kind of more correlated with one another closer together, you start to see much more structure emerge. And so that's what's shown here. This is the average matrix from all subjects, all sessions. Just showing you it bigger here. And I have applied lines here to demarcate which regions are part of which network. Now, one question is, how do you come up with those lines? And how do you decide this set of regions is part of network A or this set of regions is part of network B? So what I've done here is actually apply a known network or known previously published network decomposition. Based on the Gordon 333 atlas. And this was this network decomposition, which I'll talk a little bit about how they sort of determined that different regions were part of different networks in a second. But this network decomposition was actually done on a separate data set of 120 individuals at rest on average. But you can see that in this other data set, it still does a pretty good job of identifying blocks of structured correlations within the data. And so one thing that's nice is that once you have these blocks of structured correlations, you can also sort of look for features of those structure that might be a little bit more detailed. So yes, you tend to generally see high correlations along the diagonal, so that's high within network correlations, and lower correlations in the off diagonal, but that's not entirely true. So you'll also note that some of these off diagonal blocks can, for example, show relatively high correlations, the remaining. So for example, the cingular-opercular network, or CO, tends to still have fairly high correlations with motor and auditory related systems. It lies fairly close to them. Other things you might know is that the default mode system, while having negative correlations with many other task positive systems, is not equally true for all task positive systems. So they're most negative with the dorsal attention and the cingular-opercular, and actually shows a mix of positive and negative connections with the frontal parietal network. So there's actually a fair amount of structure and information you can get from even this fairly simple representation of brain networks. So let's just talk for a second about community detection. And I think you'll be hearing more about sort of clustering algorithms and community detection algorithms in the next talk. I'm just going to very briefly introduce a few ideas and resources if you're interested in probing into this further. So as I said, these lines were sort of demarcated based on this Gordon 333 definition of which regions are in which network, which is shown in these colors. The parcels themselves are also kind of outlined in gray. And there are various different approaches that might be used for community detection, and if you're interested in getting into the nitty-gritty, I really encourage you to read through this Fortunato paper, tome really, it's like a 70-page paper that gets into a lot of detail about all the different sort of approaches that there are for community detection, their pros and cons, what sort of networks they're good for, sort of what strategies they have. I think there's actually an updated version, this is the 2010, but there might be a more recent sort of, he's added a few more things to this paper as well. And so just to briefly talk about a few that are commonly used in resting state world. So one is called modularity maximization. And so this refers to maximizing the modularity of a given graph. So this graph is not modular, so it would have a low modularity. This graph has nice clustering within it, so it would have a high modularity. And the equation for modularity is shown below here, which is actually just looking at essentially the number of connections that there is within a system compared to the expected value that you would expect for that system given a particular set of degree distribution to the graph. And so you can maximize this equation in different ways. There's kind of faster ways and slower ways to do this and try to search for the optimal strategy for dividing up a graph into different networks. And so this is used by many groups. What we actually used in that other paper, and we've often used, is a slightly different approach, which is called Infomap. So this is an information-based criteria for defining networks in the brain. And so with this criteria, you sort of start with this idea that you might have a random walker that you drop down at places in the graph and let them walk around the graph. And so some places they'll walk around more frequently than others. And then you'll do what's called a Huffman code. So you'll give a code to each region that the walker walks through, and you try to minimize how long it takes you to tell or write down how many nodes it's gone through. And so in that way, you give shorter codes to things where the places where that walker walks more frequently. And sort of the insight that Roswell and Bergstrom had is to actually apply this code 2 times. So they have a 2-layer Huffman code. And so they first actually give general zip codes to different clusters to further reduce the amount of information that's required to encode the path of this random walker through this stream. And so, for example, if you say everything in here is 111 to start with, we've walked into area 111, and then we'll give them kind of short codes within that. And then you can reuse the codes in another area. So this is kind of equivalent to the idea that 2 different cities, like Chicago and Seattle, might both have the same street name, like a Broadway somewhere in it. So you can reuse the name Broadway because we now know that they're in 2 different cities and we have that general piece of information. And so this equation and the code to apply this equation can be downloaded from their website, mapequation.org, and it's described in more detail in this PNAS paper. So that just gives you a very kind of brief overview of community detection. But let's actually now make matrices for different sessions of a subject and for different subjects. So that's what this next 2 sections are doing. So let's start with first subject. I'll try to put the group over here. You can still see it. So this is subject 1, session 1. And so you'll see that this subject's correlation matrix looks kind of like the group. There's still a block diagonal structure in that individual subject. But you'll also note that they differ in a number of ways, and you might be able to pick out certain features that seem like distinct. For example, this subject seems to have this like little piece of the somatomotor system that's doing something a little different than what you tend to see in the group. It kind of pops out as a stripe. And so we can now walk through different sessions, and you'll see that that stripe is pretty consistent across the different sessions of that subject. And you'll note that many of the individual features don't look like noise in sort of at least the random sampling sense, because they appear again and again across sessions. If instead we now plot data from different subjects, so I'll kind of walk through that, you'll note that each subject, again, replicates the pattern that they're similar to the group, but they also have their own unique features that might not be similar to one another. And so you can make all of these graphs for each individual subject. Okay. And so just to show you kind of all of that in one place, you might, by eye, sort of get the impression that if you were to plot different subjects, they're more different from one another than same sessions from the same subject. And so in the next part, I'll actually have you do that and sort of quantify that more directly by just looking at the similarity of the correlation matrices across all of these different forms. Okay, and so you make this similarity matrix here, which is organized first by subject, and then within that, each of the 10 sessions from each subject. You've just taken the upper trie, so the unique piece of each correlation matrix, and correlated them to one another. And much like the work that I was showing you earlier, this doesn't include task data. Oh, and just as a note, this is another matrix, but it's not a correlation matrix in the same sense as before. Now, any given unit in this matrix is a similarity between a pair of correlation matrices. So don't mix those two up. This is like one level higher up. But you'll note that there's a lot of structure to this matrix. So first off, there is a block diagonal structure here as well. So that indicates that a particular person's matrices are most similar to themselves and distinct from those of other subjects. So there is this like individually specific feature to these matrices. There is also other structure. For example, you'll know MSCO8 has all these blue lines that kind of go through it. And MSCO8 is also the subject that slept a lot during scans and has very little data compared to all the other subjects. So much of the structure that we end up finding of like these vertical or horizontal lines appears to be related to data quality issues. Yeah?
Me being more similar to myself than other people, do you think it's related to anatomical variability?
It's a great question. And so we looked at that a little bit in the paper I was talking about earlier. And so one thing that we tried to do to address that question is we actually took each individual subject. Here, let me see if I have the plot. So we took, instead of doing this by parcel, which is kind of hard to align, say, like one given parcel to that. That's like an interesting and difficult question. If anyone wants to sort of solve that next week, that would be amazing, and you could get back to me. But saying that, say, like parcel 1 in individual A is the same as parcel 305 in individual B is actually kind of a hard question to answer. So what we did is, in the original paper, we used these group parcellations and looked at the similarity across different elements. But then we can also look at what if we used individual parcellations, defined networks, and then compare, say, just the frontal parietal network, the default mode network, and so forth. So everybody has all of the major networks, and so we can just look at the correlation at the network level. And what we end up finding is actually a very similar pattern. The effect of group is maybe a little bit larger, but it's still a very hefty effect of individual subject. So it doesn't look like it's totally explained by individual variability and where these networks are, but I think that's still an open question of how much it might be explained by that. And just as a control, we also used the group network parcellation and did the same thing. And you'll note that this is part of what I was saying. This part of that group effect getting larger, I think, is also just about the scale of the data. So now we're looking at sort of grouped networks as opposed to ROIs. And you can see that even with group definitions, the group effect gets bigger. So part of it is, I think, a scale issue and not an anatomical variability issue. Okay, so I am out of my time, unfortunately. So I don't want to eat into other time, but I'll just show you a preview of what you would do in the last two sections. And if anyone is interested, feel free to complete them. I'll be at office hours. I'm happy to sit around and help anybody get through those. But the basic idea of the next 2 sections is I was just going to show you how to make these actual spring embedded layouts. We have some code in MATLAB to do these and make them look like that, but Gephi actually makes them look a lot prettier. So if you want, the code I provided you with is actually to make inputs into Gephi to make these beautiful force embedded layouts. They look a little different because the force algorithm is slightly different that's used across these 2. But I also provide you information on the different algorithms, and it's kind of neat because you can see it happen in real time, sort of. So just to show you, it gives you more of a sense of what's happening. So here I've already loaded some of the data. I can force it back into some circular layout like this. And then if I say I want to look at a force layout, so I force things that are kind of more tightly connected to be closer to one another. This is the reason it's called spring embedded, is like you envision that all of the nodes are connected by springs, and the springs want to be as close as possible so that they don't have a strong force, and so it squishes together things that are strongly interconnected. This one's not exactly a spring embedded layout, so it has other forces in it as well, but you can sort of see it transferring into this force embedded layout, which gives you some insight into, oh, the default mode really is more tightly interconnected with, say, the frontal parietal system than it is with, say, the cingulopercular or dorsal attention system. So I think they're kind of nice. You can play around with the parameters. They're obviously just visualization, so they will change depending on the exact threshold and other elements of how you do it, but I think they can still be insightful on the data. And so you can look at this across a number of thresholds, which I've shown here. And you can also use these techniques to make those hub measurements. And so just to show you what the final output would look like, these are the spring embedded layouts for network, where color is denoting a network label. This is where color is denoting the degree of the node. You'll see that degree is really largely based on the size of the overall network. This is within module degree, so it's a slightly different variation where it tries to do degree based on where you are within your own module, and it denote most important nodes for that given network. And then participation coefficient instead highlights nodes that lie between different systems. So it's more of a dispersion measure that tries to identify nodes that have connections to many different systems. So yeah, so come find me if you want to do any of that. And yeah, thank you to all the people that have helped with various of this work. And here's my contact information if you need it.